Hello, so let's continue with chapter 8, looking at solutions chemistry. Excuse me. Hopefully that helps a little bit from my little laundry room. So we were looking at how the amount of solute that could dissolve was affected by volume and affected by temperature, and how changing from a solid solute to a gas changed the solubility when it came to temperature, because gases are more soluble at colder temperatures. We also saw that pressure now becomes a factor when dealing with a gas as a solute. Only gases are affected by changes in pressure. Solids and liquids, when added to a solvent, are not. But to think about solutions properly, we need to know how much of the solute is in solution. We need to be able to measure the concentration of that solute. Now, of course, being chemistry and science, there's always a variety of ways to do that. We're not going to look at them all, just mostly concentrate on molarity, which is the main one used, and then talk a little bit about percentage concentration, and then briefly mention parts per million. And really, there's just so many that we just want to focus on the main ones. So if we start with looking at molarity, oh, there's Jared trying to get in. Molarity is quite literally a measure of the number of moles of solute for a litre of the solution. And so to calculate the molarity, moles per litre, we take the number of moles divided by the volume in litres. Molarity is a measure of moles per litre. So moles divided by the volume gives us molarity, or we can switch a calculation to give us the number of moles of solute. That would be taking the molarity, the number of moles per litre, multiplied by the number of litres. Or if we want to know the volume of the solution, which mainly becomes useful if we're trying to create a solution of a particular concentration, we take the total moles of solute that we have, the desired molarity per litre, and the moles divided by the molarity gives us the volume of the solution. Always start with base principles of molarity equal to moles divided by volume. So let's look at some examples. Preparing 3 litres of a 1 molarity solution of potassium carbonate. What weight of potassium carbonate would be needed? Now, our equation doesn't directly calculate the mass of chemical, but we can convert that mass into a number of moles. And so we can work out the number of moles based on the molarity and volume. Molarity times volume gives us a number of moles. That's a molarity of 1 with a volume of 3 litres. So we have 3 moles. Of course, given the chemical formula for potassium carbonate, which you always would be, for your solute, K2CO3. Potassium, of course, a 1 plus ion from group 1 in the table, as we talked about in chapter 3. And CO3 carbonate being one of our polyatomic ions from chapter 3, that's a charge of 2 minus. So the correct formula would be 2 potassiums to the 1 carbonate. For the mass, as we did in chapter 5, mass for a mole, that's 39 grams for potassium from the table, 12 grams for carbon, and then 16 grams for oxygen each time, and there's 3 of them. So molar mass is 138 grams. We want the mass for 3 moles. We've already worked that out. So 3 times the mass, that would be the 414 grams. So we can't directly work out a mass in grams, but we can get to the mass if we know the number of moles, because we can work out the molar mass. Second one, looking for the molarity of a solution with 120 grams of sodium hydroxide, and it's dissolved in 500 milliliters of water. Now for the sodium hydroxide, its formula is NaOH. Of course, we can work out the mass of 1 mole. That'd be 23 grams for sodium, just straight off the periodic table. 16 grams for oxygen and 1 gram for hydrogen. So a molar mass, as we said in chapter 5, of 40 grams. So to work out the number of moles, we take the weight, which was 120 grams, divided by the weight of a mole, which is 40. So that comes to 3 moles again. So the molarity, moles divided by volume, would be 3 moles divided by that 0.5 litres, the 500 millilitres, divided by 1,000 to turn it into a litre. That gives us a molarity of 6 molarity. For every litre of solution, there's 6 moles of the sodium hydroxide solute. Third one, student with 252.5 grams of the solute, the potassium nitrate. They dissolve it in 400 milliliters of water. What would the molarity be for the solution? So of course the molarity is going to be the moles divided by the volume. But we don't have the number of moles yet, we just have a mass. So we need to know the mass of 1 mole of potassium nitrate. 39 grams for the potassium, as we said before, 14 for nitrogen, then 16 for oxygen, 3 times over. So just over 100 grams per mole. So the 252 grams divided by the mass of 1 mole that we just calculated, that comes to 2.5 moles. So 2.5 moles total. That's going into a volume of 0.4 litres. That's the 400 millilitres divided by 1,000 to convert to litres. One of our chapter 1 tools. And so the molarity of the solution is 6.25 molarity. Number 4. Student asked to take 786.6 grams of sucrose, and they're going to make a solution with a molarity of 2.25. What would the volume of water be needed to make the solution? Well, for the volume, that's moles, small m, divided by the molarity, large M. We need to work out how many moles we've got, again, because we've been given a mass in grams. You cannot use a mass in grams for the molarity equation. You need to work it into a number of moles. And we've already done that in chapter 5. So we work out the mass for 1 mole, given the formula in the question. 12 grams for carbon, times 12, because there's 12 moles in the formula. 1 gram for hydrogen, times 22, because there's 22 moles in the formula. 16 grams for oxygen, times 11, because there's 11 moles in the formula. So we get a molar mass of 342. For the number of moles, that's the total mass that the question told us about, 786.6, divided by the mass of 1 mole, the 342. So it comes to 2.3 moles. So our original problem, the moles divided by the molarity, that's 2.3 divided by the 2.25 molarity we were told about in the question. So it gives us a volume of 1.02 litres. We want a concentration of 2.25 moles per litre. We need just over 1 litre, given that we've got 2.3 moles. Okay. There's another 2 questions to finish molarity of this part. And that's a good idea to try practicing for yourself. So take a couple of minutes and try and work out the answers to these 2. And I'll go check on my baby girl. Let's see where we were looking at these problems. So we've got 160 grams of the sodium hydroxide, and that's going to be added to 2,000 milliliters of water. And we want to know the molarity of the solution. Of course, to work out molarity is equal to the moles divided by the volume of the solution in liters. And so that volume can be converted into liters by dividing by 1,000. So that's simple enough. That just comes to 2 liters. That's 1/2. But for the sodium hydroxide, we need to know how many moles 160 grams is. Well, from the chemical formula, sodium hydroxide, Na, that's 23 grams for sodium. Oxygen, that's 16 grams. And then for the hydrogen, of course, that's 1. So total is 40 grams per mole. We can now work out how many moles we've got because we've got the total mass of 160 divided by the mass of our unit, 1 mole. That comes to 4 moles. So we can plug that into our original calculation. 4 moles divided by a volume of 2 liters, and that gives us a molarity of 2. For every liter of solution, we've got 2 moles of the sodium hydroxide. The second one, calculating the mass of sodium chloride in 250 milliliters of 0.1 molarity sodium chloride solution. Of course, that volume can be converted into liters again by dividing by 1,000. That gives us 0.25 liters. The molarity is already given as 0.1. Now we can't work out the mass directly from our equation, but we can work out the number of moles. We've got the molarity times the volume, times the volume to give us the number of moles, and that will be 0.1 times the 0.25. So 1/10 of the 0.25, that comes to 0.025 moles. That's the first half. Now we need to know the mass for 0.025 moles of sodium chloride, of course. That would be 23 grams for the sodium and 35.45 grams. Is it 35.45? Why is my brain suddenly screaming at me to do 35.35? That must be 45. Let me just look up here on our table. And it's not showing me that, of course. Great. No, it must be 35.45. I think my brain's just playing tricks on me, making me think it's 0.35. Yeah, 35.45. Okay, I wasn't crazy. Good to know at my age. And so that gives us a grand total for the mass of 58.45 grams per mole. And so for the mass of 0.025 moles, we just take the 0.025 and multiply it by the 58.45. And that gives us looks like 1.46 grams. Okay. Any questions about that one or any of the ones we've done so far? Molarity is moles per litre. Some of the problems will give you a volume in milliliters, so that has to be converted into litres. Some of the problems will give you a mass of solute in grams, like you were working in the laboratory with a balance. And you can work out the mass for 1 mole with the chemical formula and work out how many moles you have. Okay, we're doing all right? Okay. Right, so that's molarity, moles per litre. And the other big one we want to talk about is the percentage concentration. Percentage concentration is looking at the mass of solute in grams divided by the volume measured in hundreds of milliliters. So we're no longer using moles, we are using mass. We're no longer using liters, we're using milliliters when it comes to our percentage concentration, taking that weight as a percentage of the volume of the solution. So the percentage is equal to the weight of solute divided by the volume of the solution times 100 to turn it into a percentage. Just keep in mind for any solutions you're making, as you add the solute and solvent together, don't start with your total volume of solvent that you desire. Start with maybe half or 2/3 of it, and then add in the solute. The addition of solute will expand the total volume of the solution. So you want to make room for all of the solute to be added, and then add enough of your solvent, probably water, to bring the volume up to that desired level. If you start with the total volume and then add the solute, you're going to increase the volume of the solution and decrease the concentration. You've got to hit your target solvent volume. Okay, so look at some examples. For percentage concentration, 250 milliliters of water containing 40 grams of copper sulfate, the solute. The percentage concentration would be the weight divided by the volume times 100. We know the weight, that's 40 grams of solute. We know the volume in milliliters, that's 250. So that comes to 16%. Basically, it's telling us for every 100 milliliters of solution, there'd be 16 grams of the solute copper sulfate. Next one, looking for the mass of CO2 that you'd have to dissolve in 1500 milliliters of water to make a 20% carbonated solution. So start with our base equation. The percentage is equal to the weight divided by the volume times 100. Now we actually want to know the weight of the solute this time. So if we rearrange the equation, the volume moves across the equals, so it becomes a multiplier instead of a divider. And the 100 moves across the equals, so it becomes a divider instead of a multiplier. So we get the weight of solute equal to the volume times the percentage divided by 100. That comes to 300 grams. Fairly straightforward with the percentage concentration questions because we don't usually have to think about the moles. Next one, looking for the volume to make a 30% solution of sodium nitrate. You've got 80 grams of the sodium nitrate to use. So remember, the weight divided by the volume times 100 gives the percentage. So for the volume, that would be the weight divided by the percentage times 100. The weight, of course, is 80 grams. The percentage is 30%, then times 100. That would be a volume of 266.67 milliliters. Take a couple of minutes and try the next one. the mass for sodium fluoride if we're making a 20% solution in 400 milliliters of water. Remember, homework questions are still up for Chapter 7. They'll finish tonight. People can take the exam for Chapter 7 today in the Learning Lab until Friday.
Right now, hey Harrison, right now, we're at almost max capacity, so our student lounge has been converted to a small classroom.
Sounds like I'm not the only one who's trying to work from home. Ah, I let my tea go cold. What a crime. Oh, okay. We'll stop that. Chapter 8 homework should be up by midday tomorrow at the latest. I might get round to it tonight, but I do want to take a look through the questions and maybe add a few extra to the pools. All right, let's take a look at this one. So remember, from base principles, always start with the original equation itself. That can help get our thinking going. So the percentage is equal to the mass of solute divided by the volume of the solvent. This is one of the things that trips people up. Be very careful and distinguish between the solute, which is a small amount of chemical, added to the solvent, which is a large amount of chemical. So the mass of the solute divided by the volume of the solvent times 100 to give us a percentage concentration. Now we've got the percentage, we know that. We've got the volume. What we're really looking to work out is actually the mass of solute. So rearranging our equation, the mass of solute is going to be the percentage concentration multiplied by the volume divided by 100. So percentage, that was 20%. That's 20% per 100 milliliters. Multiplied by the volume of 400 milliliters divided by 100. So that gives us 80 milliliters. Oh, sorry, 80 milliliters, I beg your pardon. 80 grams of the solute. Okay, any questions about that one? Molarity is dealing with the number of moles in liters of solution. Percentage concentration is dealing with the mass in milliliters. Be careful. And always distinguish between the actual solute and the solvent. Okay, let's see how we're doing for the chapter. Right, let's see. So we are going to break the chapter down a little bit and spread it out into next week as well, because two of the sections don't have all of their lecture this week. So let's see. How much should we do today? I think we'll do a bit more just to be on the safe side. So if we don't have much to do next Monday to finish off, that's fine. I'd rather do less than more on Monday next week. So let's do dilutions. That's something that's quite often done in hospitals because the solutions which are bought in by the hospital are often bulk concentration. And then it's just a case of adding in water to dilute, like you would dilute your orange juice, to the desired concentration for the patient. So this has to be done right. You don't want to give a patient a drug at the wrong concentration. So when we do a dilution, we're quite literally just adding in water. So whatever the concentration was to begin with, the number of moles of solute isn't changing by adding water. You're just diluting it. So whatever the number of moles was before, by taking the molarity times the volume, which we could describe as M1 times V1, the initial concentration times the initial volume, that's going to be equal to the number of moles after water has been added, because as the molarity, the concentration decreases, of course the volume of the solution is proportionally increasing. So we'll still have the same total moles of solute by the end, M2. And so we can say that over that dilution, M1 times V1, which gives us the initial number of moles, is equal to M2 times V2, the final number of moles, because it's the same thing. We're only adding in water, which is acting as solvent. We're not adding in any extra solute. So we'll quite often pose the question as to how much water has to be added to perform that dilution. Keep in mind that V1 is the initial total volume of the solution, and then V2, which you'll often initially calculate, is the total final volume of the solution. But that V2 includes V1, the initial volume. If you want to work out how much water has been added, you need the total final volume V2 and subtract the initial volume V1. The difference between the two is the amount of water, the amount of solvent which has been added. So if you're trying to work out how much water to add to dilute your chemicals, V2 is not your answer. V2 is that final total volume. V2 minus V1 is the amount of solvent you're going to add. So let's take a look at some examples. So with a concentrate of 400 milliliters of 12 molarity hydrochloric acid, you're told that the new concentration after dilution has to be just 3 molarity. What volume of water would you add? Well, we start with a base equation, M1 times V1 is equal to M2 times V2. We've got the initial molarity of the concentrate, that's 12. We've got the initial volume, 400 milliliters. Now, standard units for liquid, of course, as we saw in chapter 7, is liters. So we can convert that by dividing by 1,000 into 0.4 liters. The final molarity desired is just 3 molarity. what would be the total volume of the solution, and therefore how much water will you add. So V2 would be M1 times V1 divided by M2, that free molarity. That gives us a value of 1.6 litres, but the original volume of the solution was 0.4 litres. So subtract that volume you already had, the amount of water added is just 1.2 litres. V2 is the final total volume, but the amount of water you add is the difference between V2 and V1. Next one, this time 600 milliliters of a solution at a concentration of 5 molarity for sulfuric acid. If you want to make it to a molarity of just 2, how much water would you add? So again, M1 times V1 is equal to M2 times V2. We know the initial concentration of the acid, 5 molarity. We know the initial volume, 600 milliliters, which we divide by 1,000 to turn into milliliters. And we know the final concentration desired, 2 molarity. So V2 will be M1 times V1 divided by M2. That gives us 1.5 litres. And so the amount of water added to the 0.6 litres would be 0.9 litres, 900 millilitres. Number 3, a little bit trickier because you're told that you want to prepare 1 litre of 2.5 molarity nitric acid from an initial concentrate of 8 molarity. So you know M1, you know M2, and you know V2. The only thing you don't know is V1, the initial volume of the stock solution you're going to take for this. So to calculate V1, it'd be M2 times V2 divided by M1. That gives us 312.5 milliliters or 0.3125 liters. Factor of 1,000 between liters and milliliters, of course. We subtract that from the volume of the final solution desired. So we start with 0.3125 liters of the stock solution, and we're going to add, again, the difference between V2 and V1, 0.6875 liters to get to that 1 liter concentrated solution at 2.5. Let's see, a couple of practice questions to finish off, 2 of them again. Let's try and get them on the same page. So we'll call this our finish point for today. What would be the answer for these 2? What volume of water do you have to add to 600 milliliters of 12 molarity acid to the concentration of 4 molarity? And what would be the final molarity for 400 milliliters of 10 molarity sulfuric acid stock if you added water to dilute and it had a final volume of 1200 milliliters? Take a couple of minutes to try those. I'll check on my rambunctious daughter and then we'll call it a day once we check our answers. Even the cat's giving me a hard time. Okay, let's finish these off. So of course, for these dilutions, our calculation it pays is M1 times V1 is equal to M2 times V2. Let's see, what volume of water would you need? We've got 600 milliliters of the initial solution, or 0.6 liters. The initial concentration is 12 molarity. And we want the new concentration, M2, to be just 4. So V2 will be the 12 molarity times the 0.6 liters divided by the 4 molarity that we want. And that comes to, let's see, 1.8 liters. Now that's going to be the final volume of the entire solution. But we had already started off with 0.6 litres at the beginning. So the amount of water to add to perform this dilution will be just 1.2 litres. Add 1.2 litres to the 0.6 gives us 1.8, and that will give us a concentration of 4 molarity. Any questions about that one? Making sense? Usually the molarity is one of the easy things in the chapter. It tends to be molarity calculations and percentage concentration that gives us one of the big problems. Oh, don't really need to put that off. Let's see, second one. What would be the final molarity for 400 milliliters of 10 molarity stock if we had water added to dilute to a final volume of 1200 milliliters? Okay, a little bit different. So this time M1 times V1 equal to M2 times V2, of course. We are looking for the final molarity. Okay. We've got the initial molarity, which is 10. We've got the initial volume, 400 milliliters, which is 0.4 liters. And we want to find out the final concentration, M2. And we want a final total volume of 1200 milliliters, or 1.2 liters. So that becomes, for M2, that'll be the 10 multiplied by the 0.4 divided by the 1.2. And the numbers are a little bit tricky at this time, so let me check. Equals concentration of 3.33 molarity. No need for V2 minus V1 because we're told the final volume. So of course, to do that must have been 800 milliliters added to the 400. But 3.33 molarity is the concentration. Any questions on this stuff we've done today, or anything we've done together this week, excuse me, this week so far? You don't have to just ask questions on what was specifically done today. It could be anything in the chapter. Remember, there's office hours every night at 9:30. I've got those practice exams. Looking online this morning, we're just 2 days away from the final exam for some people, and only 4 people have tried the practice test for chapter 7. People are leaving their studying for each chapter way too late. You cannot fully prepare and absorb material just 2 or 3 days before the exam. We started chapter 7 over a week ago, almost 2 weeks ago. Okay. Right, I'll leave it there. Have a good lunch, stay safe, wash your hands, and wear that mask.